Alright, in this video, I'm going to be working some gradient and directional derivative examples. I'm going to be working through Form P of the Multivariable Calculus Quiz 2.5. So, I let y'all work in groups on this, and I gotta think in future years I'm going to do the same thing. So when they ask you about the maximum rate of change, that's the length of the gradient vector. Okay, and we need to be able to just like translate that. So let's say, what is the length of the gradient of f? I think a thinner pen will do good for me. So I've got this, and so really what I'm doing is taking the length of the vector 7, 8, 9. So that's 49 plus 64 and 81. And let's see, 49 and 81 is going to be 130, plus 64 is 194. There you go. All right, and that's the maximum rate of change of the function. Right? They're just asking you for the length of the gradient vector just encoded in an unclear way. Okay, but now you know. What is the value of the directional derivative of f in the direction of u at the point 3, 4, and 5. Okay, in class, this one caused a lot of issues, mainly because of that. And so I'm really glad that I put this on the quiz, because this is very similar to a prompt from one of the multiple choice questions I'm going to use on you. Okay, what I'm proposing is that u is already a unit vector. Okay, if you take the length of -1, 0, and 1 as a vector, it doesn't really look like absolute values, but that's going to be the square root of 2. So that's what they did. They just factored it out on the outside. Okay, so u is already a unit vector, so I don't need to, like cut it down or anything. I'm going to just say, all right, well, the derivative of f and the direction of u at 3, 4, and 5 is going to equal the gradient of f at 3, 4, and 5 dotted with u. Okay. Now I've got the gradient of f at 3, 4, and 5, and that's 7, 8, and 9. So I'm going to say that's 7, 8, and 9. Now if you want to hold on to that 1 over the square root of 2 on the outside because you're really good with your dot product properties, you can do that, but if you're unsure, just distribute it in. It's not a big deal. Okay. And then when I actually dot these, I'll get -7 over the square root of 2 plus 9 over the square root of 2, which equals +2 over the square root of 2, which I might point out to you is also equal to the square root of 2. And it's something that's kind of come up recently in my pre-calc class. 2 over the square root of 2, same number as root 2. All right, number 3 is asking for an example of a vector that causes the directional derivative to go 0. Okay, well, what I think we should do is just find the gradient of f, think about what could I dot this with, and then we'll, see something. And it was pointed out to me in class today that I probably needed to say non-zero there. And so, probably the quiz you're looking at, might say non-zero on it. All right, so what was I thinking? Oh, I need fx, the derivative with respect to x, and so that'll be 3e to the y minus 2y e to the x minus 1. Fy is going to equal 3x e to the y, because e to the y is its own derivative, minus 2e to the x plus 1. So if I want the gradient of f at the point 0 and 0, well, that's just going to be whatever happens to fx when I plug in 0 and 0. So I'd have 3 minus 0 minus 1 is 2. And 0 minus 2 plus 1 would be -1. Okay. So I've got that, and I just need w to be some vector so that... I'm going to actually write it out. 2, -1, dotted with some vector w, which is w1 and w2, that needs to equal 0. So pretty much, that would be 2w1 minus w2 equals 0. Just as long as the second component is twice the first component, this will work. And that actually makes a lot of sense. One example for w would be the vector 1 and 2. Right? Because if I dotted that with the gradient vector I'd get 0. And, you know, cutting it down to a unit vector isn't going to change the direction, isn't going to change the orthogonality. It's still going to have dot power x 0. Okay, so over here, I've got w equals 5x squared y. Find the value of the gradient of w at 1, -1, and 2. All right, so I'm going to need to find my partial derivatives. Wx is going to be 10xy minus 0 plus 0. Okay, that was easy enough. W with respect to y would be 5x squared minus 8z. And then the derivative of w with respect to z is going to be -8y plus 3z squared. And then I think what I should do is probably plug in my 1, -1, 2 to all of these, and then, you know, see what happens. So 10 times x times y, that's going to be -10. W with respect to y with, okay, x equaling 1, that would be 5 minus 16 is -11. And then -8y is going to be positive 8 plus 3 times 4, 8 plus 12, that's going to be 20. So I'm going to say gradient of w at the point where x is 1 and y is -1 and z is 2 is going to be the vector -10, -11, and 20. And hopefully I've done a good job so far of, you know, displaying my vectors in different ways and reminding you that you can write it vertically if you really liked linear algebra, or you can write it, you know, like a point if you want. You don't even have to use the pointing brackets. I don't know what you mean. So for the function g, which is given by x, y to the third, z to the fifth, find the maximum rate of change, okay, again, and the direction of maximum increase. Okay, so the direction of maximum increase, that's the gradient. Okay, I don't want a red highlighter. Right? So that's going to be gradient g at any point, maybe I'll just write that out, is going to be, with respect to x, if I take the derivative, I'd have y to the 3, z to the 5. If I take the derivative with respect to y, that would be 3y squared, so 3x y to the 2, z to the 5. And then with respect to z, it's going to be 5x y to the 3rd, z to the 4th. Okay. Now, the direction of maximum increase when x is 3, y is 1, and z is 1 is going to be, I'm just going to plug in on that, y to the 3rd, z to the 5th, that's going to be 1. 3 times x is 9 times 1 times 1, okay, that'll be a 9. And then 5x is 15 times powers of 1, okay, 1, 9, and 15. Okay. Now, if I want to find the maximum rate of change of g, that's the length of the gradient vector at 3, 1, 1. Okay. Well, the length of that vector is going to be the square root of 1 squared plus 9 squared plus 15 squared. Okay, I'm going to do the 225 plus the 81 first, and that'll be 306, and then I add one more, and that's 307. Yeah, okay, and that is maximum rate of change and direction of maximum increase. Okay. I think it makes a little bit more sense to find the gradient first before you plug in on it and find the length. Okay, find the gradient of this thing. Okay, well, it's had to have one of those. We'll just use the word gradient. Gradient f is going to be, you know, fx and fy. Okay, so I need to take my partial derivatives. I think I'm going to rewrite f of x and y. If I've got something in the denominator, that's x squared plus y to the negative first power. Okay, fx, okay, just observe the chain rule, do the power rule first, negative of that thing to the negative 2 power times the derivative of the inside with respect to x. So that's going to be 2x. And so the inside stay the same, and then f with respect to y, okay, the same thing will happen here, but then I'm going to multiply by the derivative of x squared plus y with respect to y, and that's just going to be 1. So this is going to be the vector that has negative 2x over x squared plus y to the 2 power, and then negative 1 over x squared plus y to the 2 power. Okay. And the last one is for this function here, which is y e to the negative x plus 5z. Find the maximum rate of change of h and the direction of maximum increase. Okay, we're familiar with that prompt. Okay, direction of maximum increase is going to be the gradient of h. Okay, gradient of h with respect to x, I would have negative y e to the negative x. And then 5z doesn't depend on x, so its derivative would be 0. Okay, with respect to y, well, e to the x, or e to the negative x is just a constant, so I'd have e to the negative x, and 5z is constant with respect to y, so let's leave that there. And then the last one would be, with respect to z, that derivative would be just 5. All right, so gradient h at the point where x is 1, y is 0, and z is 2, well, it'd be y is 0, e to the negative 1, and 5. And then if we want the maximum rate of change of h, then we're going to be saying, all right, well, the length of the gradient of h at 1, 0, 2, it's going to be equal to the square root of 0 squared plus 1 over e squared plus 5 squared. Okay, now if I had to have, I think that's good enough, or you'll be able to recognize the right answer in a multiple choice setting. But if a person did feel like they needed to, like kind of simplify this a little bit, I think we could call this 1 plus 25 e to the 2, all divided by e to the 2 inside the square root. Okay. And if we wanted to go a little bit farther than that, we could say that's 1 plus 25 e to the 2 divided by 1 power of e. Okay, but I don't know that any of these are necessarily more simplified than the other, or definitely not any better than the other. And so that's going to be all for this one. Yeah, that was a good collection of gradient and directional derivative problems, especially if you're gearing up for a multiple choice test in my class. So that's all. Thanks for watching.